So what I wanted to talk to you about is computer-aided discovery as a field. And I got into the area of geophysics and astrophysics out of curiosity, meeting people who described to me there's all this data and all these challenges and how to generate knowledge out of this data. And I was thinking this is very interesting to develop new methodologies that can push actually two areas. One area is, of course, the applications in astro and geophysics, which are very interesting and challenging. But at the same time, we're going to push computer science because we are working at the frontier trying to harness data from different sensors all across the planet. So we have sensors deployed on the ground. We have satellites gathering images at various wavelengths all the time. And then we have telescopes on the ground and in space looking far away into the universe. And certain problems in this context are very similar. It doesn't really matter if you're doing astro or geophysics. Once you're looking at time series, for example, and looking for features and insight generation from time series, it's very well applicable across a variety of domains. But for this specific meeting, I'm going to focus on our work on the geoscience area, just to give you a little bit of context of where we are right now and where we are going. So we are facing many frontiers which require machine assistance. So classically, scientists are used to go to a big data repository or an FTP server, pull files, do something with them, and that era is over. We're talking in astronomy, for example, petabytes per second. That's over the next couple of decades for a subset of instruments that are being built. So petabytes per second level science means even if you have algorithmic automation, you still end up with a gap in how you interpret those results. So we need to think about the stack. How do I get from the actual science question to the data collection, to the analysis, and more importantly, to the interpretability of this data? Because we're facing cognitive limits. We have limited time, we're focused, we have biases. So we clearly need something that helps us with this challenge. So I want to present you a framework that we found pretty useful in the way we approach the different algorithmic perspectives. And this framework comes from semiotics. Actually, this has a lot to do with communication theories, but I thought it's very useful in the science area as well. So if you're looking at what we're doing with real-world phenomena, we're gathering data. So at this very low level, we have signals, but the data level is essentially a syntactic layer. This layer ensures that we're collecting the right data and the numbers correctly encode what is a counterpart in the representation in nature. On top of that, we have a semantics layer, which currently is populated by data exploration techniques, data science in the sense of data analysis and data mining. And if you're taking a step back from what's going on here, is mostly we're looking to classify features or identify features that have a meaningful representation in reality. Okay, so we want to know if I see a certain spike in certain time series from an instrument, then that might be an earthquake. Or if I see certain types of clouds, they might be related to an atmospheric event, and so on. And this is where I would say many of the deep learning approaches that we see today are in this layer. And of course, there's a whole zoo of techniques that I don't have time to cover, but I will give you examples of what we have done and where the limitations are in terms of insight generation. And then I think the next challenge for everybody is the pragmatics layer, because imagine you have the perfect solution in the semantics layer, so you can classify any kinds of events that you can think about with 100% accuracy. What's going to happen? You're going to end up with billions and billions of features. So what do you want to know? You want to know, is that something new that I just found? Does it contradict a theory that was around? Is maybe Einstein's theory of relativity wrong? Does it have to be corrected? If so, how? So these are more deeper questions that now require you to have a lot more knowledge and a lot more sophistication in order to find an answer to something like that. And in the next 10, 20 minutes or so, I want to give you an example of where we are today in the semantics layer and show you an example of our work. Assume you use deep learning to solve a problem in this layer. What would it look like? And I want to show an example of how we have developed deep learning techniques to find atmospheric turbulence. And this is a little bit unusual. I wanted to show an example that you don't see all the time. So I don't just want to talk about image recognition or applications you've probably run into. And I also want to show you that we can apply deep learning to satellite imagery. But in geoscience applications, we can leverage information from different types of instruments. So data fusion makes a lot of sense if you want to increase the accuracy of a detection of a phenomenon. And in this case, we're going to combine satellite imagery and GPS to detect atmospheric turbulence. And in particular, I'm talking about Lee waves, which you might have seen if you were taking the plane on your way here. You look outside the window, you might see these ripple patterns in clouds sometimes. And these are the Lee waves we're going to detect with a neural network. What happens conceptually is that you have mountains, and in certain conditions, you can have standing waves that are being built up close to mountains. And the reason why you want to know that is that they have turbulence. So you have turbulent air over here, which is dangerous for aviation. So it's important to know where these turbulent conditions are. And of course, it's important to know when you don't have clouds. And this is where GPS comes into play, because it turns out if you use GPS signals that come from the satellites, they penetrate through the Earth's atmosphere. And in this turbulence, you also have water vapor that is being trapped. So you have variations in water vapor, and this water vapor impacts the GPS signal. So you would see delays and outliers that impact your GPS positioning if there's turbulence. And I want to show you like an example end-to-end where you see the physical counterpart and then how that merges into the machine learning as a little bit of a different perspective to make you aware how this is connected with reality. So this is where you would start. So this is how geoscientists start looking at the problem. Okay, so they're looking at time series, and these dots here are GPS stations near the Sierra Nevada mountains. And this was actually a student doing a bachelor's thesis trying to look at deformation phenomena, and then suddenly she realized that these deformations are off every now and then. And what you're getting from one GPS station, these are geodetic-grade GPS receivers that measure displacement at millimeter level accuracies. So what you're getting is time series in 3 spatial dimensions, like up and 2 other spatial dimensions. And this is an example of the time series pointing north and east, and the vertical displacement from one station. And then it turns out, well, sometimes you have these weird residuals. And when you start looking at this in greater depth, you suddenly realize, well, something has been going on with the wind direction, because these are days when you're looking at the wind direction, if you don't have a Lee wave versus when you have a Lee wave, you see an indication that these outliers only occur on days where this wind direction is pointing into specific directions. So Catherine, who did this work, took the time to investigate, and she actually found this physical connection between certain types of skewed outliers in your GPS signal and the Lee waves. So now what can we do with this? We can take this to the next level. So this would be the automation part, where now you've seen this connection, and now you want to scale it out to all the GPS stations that you have, all over the US, ideally all over the world. And this is the automation that we're achieving here. And this setup combines two instruments. One instrument is the MODIS satellite. That is a NASA satellite. There's a lot more detail that is not important here, but you're getting pictures like this. And in some of them, you would see these tile patterns that you want to identify. More importantly, you have a spatial dimension here. So this axis and this axis has a spatial meaning, so you can pick a pixel and identify a position on Earth. Now, the other thing that we have is we know where these GPS stations are located. So now we can pick the time series for these particular stations, those stations that are inside Lee wave regions and those that are outside of Lee wave regions. And initially, of course, we don't know which ones are which. But if you're looking at an outlier score, like for these skewed outliers, you would see certain features in these time series that are due to Lee waves. And now the question is, how do we combine this to build a detector that actually finds these regions and then uses the GPS stations as an additional way to confirm that that is a real phenomenon and not an artifact? So the approach here, how do we apply deep learning in this context? So what you would do is you would tile up these images, and you would have training sets that would allow you to train and say, well, I know what a ripple pattern looks like, and that's where the scientist comes in. So the scientist would say, I give you examples of tiles where there are Lee waves, and I give you examples of tiles where they're not. And notice this is not that trivial, because you can have rotations, you can have different scales, and sometimes the images can be quite large, and the regions that have Lee waves can be very, very small. So with this, you would train the network, and I'll show you in a bit how that is happening. And then the second part is combine that with the GPS outliers to really identify these phenomena. So the neural network that works in this particular case is one that has an architecture like this. So you would take the images, and it's a classical convolutional neural network. So this is actually the thing that made the convolutional deep learning networks so famous, because this is the trick. It turns out that convolution, applying the convolution on an image, is a good way to identify features that are relevant in the image. And when you're applying the convolution, you're actually having a convolution matrix that is configured with different kinds of weights. And in specific instances, with specific weight configurations, you're actually implementing a Sobel operator or operators that are very good at edge detections in certain directions. It's very similar to Jacobi iterations, if you're familiar with that. That would be also useful in solving partial differential equations numerically. But I think the key issue is that what you're trying to do is you're trying to find these features based on the convolution and find, like in a first step, find what are the relevant features. Spooling takes the result of this convolution, which is, again, a matrix, and tries to slide another small matrix over it and find the maximum. So this is kind of like a quantization, if you want, like a regional quantization. And then you can generate another layer with convolution and max spooling and until you're satisfied. So it's actually an art right now. How exactly do you design these networks? And people have different approaches, but the idea is that with a deep learning neural network, you're trying to create a classifier that separates things from the input. And if you're looking at what you're doing, it's mostly linear. So you're multiplying things with weights, and you're adding things up, and you're feeding them through a transfer function. And if that is not enough, you add another layer that adds another more specific separation, which is why they're used in practice, because you can scale it in this way. If you don't have enough layers, you just keep adding more layers and more neurons. OK, so in the final layers, you actually want to have a result like yes or no. So is this image an image that shows you Lie waves or not? Or in particular, this tile, is that a tile that shows you Lie waves or not? And then you're getting a neuron that gives you a value between 0 and 1 for yes, and between 0 and 1 for no. And then you're hoping that after you're training this network well enough, you will have an answer that is pretty clear-cut, like maybe something 99% yes and 1% for no. As you will see in the results, this is promising for future geoscience applications, because you're leveraging information from different types of instruments that look at the same phenomena, with different eyes if you want. OK, so yeah, if you were to expand this, this is what it would look like. And then you're getting results like these. So you actually have the neural network detect these patterns spatially. And these are some numbers that I just wanted to show you for completeness. So we had a pretty extensive training set of 300,000 tiles. And the test set was 20,000 tiles. And if you're looking at how well did this network classify these events, on the 20,000 tiles, it was like 96% correct. And if you were to interpret this back into the geophysics world, that's what you would get. So you would get all these stations, and then if you superimpose the red ones and trying to identify the area, the red ones would tell you where you would see Lie waves. And that happens to coincide with the meteorological reports that you get to see. Yes?
Back to your diagram, how you, sorry, I sort of miss how you integrate your information to that convolutional network.
How we what?
You have like pre-processing like part like at the end, and you have a convolution network on top, right? And your convolution network is also like yes or no, right?
Mm-hmm.
Then how you use that actual information to help your convolution network? I sort of miss that. Yeah, this one.
Yes. So this would give you like an answer per tile, whether you see a Lie wave or not.
And your outlier detection in that.
Oh, and the outlier, so if you happen to have a GPS in this tile that also says, yes, it is a Lie wave, then we combine that information. So I skipped that step, actually. So we have a function that weighs both answers and combines them into one final answer. OK, so I think that I'm trying to make the point here, just showing you this example. This is an example that you can do basically on a lot of data in geoscience. And the other key thing we need to work on is theory and insight generation. So we need to go beyond just the feature detection and now think about how do we create theories and how do we link the theories to practical applications. And this is what I want to spend some time right now. What can we do in the pragmatics arena? And I want to show you what we have tried so far and how we have made a new discovery in volcanology by applying this framework. So taking a step back here, we're looking at empirical data so far, but we want the connection to the theory. And typically, that spans a search space. So you have a search space on the empirical side, and you have a search space on the theory and model side. And if you pick one model, you have a search space defined by different parameters. So here's a model of an effect that you would see in the Earth ionosphere, which just happened to have an arm like that. It's called a tongue of ionization. And this is a simple model with two parameters. So depending on how you're configuring those parameters, you might have a model generating a different shape for the phenomenon you would expect to see. This is a carefully chosen example where I know this happens in reality. So this is what you would see in reality with different types of instruments. But if you don't have this model knowledge, and just apply the neural network to find any of that, you might probably not find it like this, okay? Your neural network would probably say, well, I see something that's circular here, or I see something that has an interesting gradient over here, or I see some pixels that might be interesting for you, but it doesn't have this domain-specific knowledge infusion. And that is important. And the other reason why you want to think about search spaces is that even on the empirical side, you have a choice in how you configure your workflow. So the workflow from the raw signal to a data product that it would use to make a new discovery is already prone to intuition. And to illustrate that, I want to show you the same exact data set on this side. This is, again, ionospheric total electron content that we got from GPS. So each pixel tells you how many electrons you have in the line of sight, like vertically on top of you. And depending on how you choose your filters and the parameters for these filters, you can make the exact raw data set look very different. And why is that? Because you might be interested in large-scale phenomena. So then you would configure the filter to think that this small-scale stuff is noise, which would be filtered out. Or if you're looking at smaller scale phenomena, then you would probably de-emphasize something like that. And if you're making the wrong choice in a complex pipeline, you can filter out everything and see nothing. And that's actually a pretty common case in large search spaces. We've developed a technique where you can define algorithmic choice. So to be a little bit more specific, if you have an imaging workflow for radar, for example, it is typically a process that is not clear-cut. So you can choose different filters. You can choose different detectors. You might assume Gaussianity or not. And this is defining a meta model for that particular domain. So what the AI would have to do is to create an instance of a specific workflow and try it out to see if it highlights certain features of interest or not. So this defines the theory representation space, and then you can look at different model variants on different data sets to try to increase the chances that you can make a non-intuitive discovery. Okay? This is where computers can be better than humans. Instead of us choosing what we think the right workflow is, what we think the right parameters are for the FFTs or the time windows or everything, we define the search space and let an optimizer decide which ones to pick. And this was actually a key that led to our discovery later, because the system tried out parameters that were uncommon in the area. OK, so we actually built this with the help of NASA and NSF. So it's a cloud-based system that accesses a variety of data sets. And it has an API, and it's based on Python, so the scientist sees Python. So everything I'm talking about is something you can actually build. And we also have a way that I'm going to illustrate in a moment to compare different models and theories and how similar they are in the types, in the terms of results that they produce. So with that, I want to show you this concrete example in volcanology to make it more clear. So this is an example where there's a lot of volcanoes in Alaska that have GPS sensors deployed on them. So actually, there's a geologist flying out and planting them at a specific location. And then you're getting time series in 3 spatial directions from each one of those sensors over a long period of time. So there's the plate boundary observatory that has data on the internet for over a decade. So you can go back like over 10 years and get all this data. And what can you learn from these time series? Well, from all these time series, you can apply a transform and see if the volcano inflates or deflates. And this is important to understand because when volcanoes erupt, they inflate before that. And the inflation is just one predictor out of others, because there's also gases and other things going on. But from these time series, if you have the right detector, you could predict the eruption. Now, the trick is Not all inflation events lead to an eruption. And there's also all kinds of events that might not be inflation. And the approach that worked for us was to be able to infuse domain knowledge and eliminate the known effects, eliminate the known trends, because there's trends in inflation and deflation that just depend on the time of year. So this is the trend removal. Then there's snow removal. Then there's various kinds of denoising. And that's already where the alternative space is starting to get bigger. Okay? You can use Kalman filters or median filters or other filters. Then, as you progress in this processing pipeline, you're getting more abstract. So from the time series, what you want to get is a model like this, where you see the main forces that are applied on this volcano. So as imagine there's a magma chamber underneath the volcano that inflates. So then on the top, you would see these GPS stations being pulled away, like in these arrows here. Imagine these arrows being forces applied to these stations. Now, that is something that you need because now you want to do an inverse model to estimate where is this magma chamber, how big is it, and how is it going to inflate as time progresses. And that is an ill-posed problem because, number one, you don't have many measurements over here, so that is sparse. Number two, you have a lot of variation depending on the choices in this workflow and the parameters just for the pre-processing until you get these forces. You can have already different kinds of models that come out at that stage. And that is actually the starting point where you would fit a model like a spherical model or a point source or something that looks like a pipe. And these are all common models in volcanology. So typically, there's no preferred choice. So it's typically good to know which one to choose. Try out all configurations because we have a small enough search space in this particular case for illustration to show you what happens if you choose different configurations and how similar are the vectors that are produced by this model. And the similarity is just measured by the difference, like the Euclidean distance for all the vectors and then summed up, right? But what it tells you is that there are models that are that could be classified in an own class. So this is actually a clustering applied to the model results. And it tells you, if you're looking at it by eye, it tells you, well, there are models that are kind of, in this white range, models that are in this black range, and models in between. So what you can do as a scientist, you can pick one representative model from each cluster and evaluate, is it really scientifically useful? And if not, you eliminate that. So you're pruning the search for the next steps. So what can we do with this? We can generate graphs like this, which show you inflation events at different scales on the volcano. We were able to successfully reproduce what was out there in the literature with automated means. But in addition, we applied this to other volcanoes, and we found new inflation events. And the idea is that, well, if you're removing everything that you know, and you're doing the inversion, and you're confident enough that it's an unusual event because it's not explained by your model so far, then if you see an increase in the amplitude in this particular event, then you found a new inflation event. And initially, we were thinking maybe it's artifacts because of all the algorithmic techniques we're employing. But we have written a paper that was peer-reviewed by volcanologists who all said that they could see this as a new discovery. So these two events were new on plate boundary observatory data that was out there for over 10 years. OK, so yeah, let me skip this a little bit. I want to touch base on a few other things before I close. So where do we go from here? I think more importantly is how do we generate theories? And we're currently working on algebra for models. So what we want to be able to do is have the computer generate models that are matched against the empirical data sets. Mostly we're employing right now genetic programming, but there's other ways to do that. And we can close the loop with current and future observations by being able to derive invariance from these models or test cases that can be used for falsification. So in other words, if you have a conceptual model like these of how the chamber might look like, then you can say, well, I should be able, if there's a GPS station up here, and this is a correct model, I should be able to see certain kinds of wave patterns that I pick up. And if not, then maybe I need to adjust some parameters or maybe even the whole structure of this model. This is a way where it can do it algebraically. This is just a draft, so potentially you can have an AI perturb a model that is already known, or add or make modifications and retest if that is consistent with the current observations. This is, again, a big search space, so a big question is how to prune these models in the right way. These are a few operators to illustrate that when you're adding or subtracting parts in this model, here, this is a model that assumes a point source that inflates, but you could choose something that's more sophisticated, or you can have a composite model. And then eventually, you might be able to derive something that's more complex like that. And hopefully, this will help us derive models that are non-intuitive for humans, but which produce better results than those we have so far. So there's a lot more to do. We've tried this also in other domains. So it works also for groundwater detection, or if you're looking at astronomy, the same meta framework is working for exoplanet search, which is an own topic by itself. But one particular example I wanted to mention where it worked is that there's a specific star called Tabby star, which has a light curve, which means the light curve, you're looking at the star and you're looking at the dip in luminosity as a planet is orbiting this star. And for most planets, this curve looks like this. Or if it has star spots or a moon, it has more dips. But in this particular case, because it's unusual, of course, people say it must be alien megastructures. Okay. So then what can you use this framework for? Well, you can say, assume this assumption was true. And you generate models that would resemble these hypothesized alien megastructures. What would their light curve look like as compared to a model that's generating debris that's orbiting this star? And this is an example that was generated with one of my undergraduate students. And it turns out this model, so after you tune and you find several model variants, this is a model with orbiting debris, which pretty well describes what you see. And the alien megastructures are pretty far off from that. And recently it was confirmed that yeah, most likely it's orbiting debris with other methods. If you want to play around with what I've shown you, this is all on GitHub. So go to github.com, MIT Haystack. Because it's cloud-based, you can even do it on your phone. And as a closing remark, because I was making this outrageous title, is can a machine actually win a Nobel Prize? And I think if we want to realize that, what did humans do? Well, these are the frequency of words in the summaries why these people got the Nobel Prize in physics specifically, and in 74 out of 130 cases, it's discovery. It's discovery, discoveries, development, method, and people giving pieces of advice how to win a Nobel Prize, who won a Nobel Prize, say things like, well, it has to open door and open our eyes. We need to see things in a different way. It has to be an unexpected result that's overlooked or ignored. And I love this one. It's better to be lucky than brilliant. Okay? So now you judge. What do you think? Will machines be able to win a Nobel Prize? And if yes, can you raise your hand? I personally believe that if we make progress in theory generation out of empirical data, that is actually a part of AI that's mostly overlooked in the current hype of deep learning. So AI is actually a much broader field. There's inference problems and problems where we already looked at how to generate theories a long time ago, but we need to revive those areas. And if we can have a theory generated by a computer with deeper insight, I think we will have jobs where scientists do nothing else than interpret a computer-generated theory and why it's so good.